So we have a reason then for the production, the possibility of it forming because we have all the components. And we have a thermodynamic reason for forming the structure because it acts as a backbone or a skeletal for the connection of other molecules which can act as antenna and increase the dissipative structuring. But how do we suppose that these molecules are being reproduced? Because, you know, today we need enzymes to reproduce DNA or RNA. And in fact, we need about 20 or 30 different enzymes for the replication process to proceed. So obviously at the beginning of life, we did not have these enzymes. So how could a DNA being replicated and produced, for example, once we have this formation of these short strand DNAs? And so we came up with this idea, which is called ultraviolet and temperature assisted replication, or UV-TAR. Okay, so as you remember, I said that the oceans at the origin of life were very warm, about 85 degrees centigrade. And that turns out that's an interesting temperature, 85 degrees centigrade, or around that, because of course the equator could have been warmer and the poles could have been cooler, but around 85 degrees centigrade. So, and that temperature is very interesting because it turns out that this is about the denaturing temperature of DNA, short strand DNA, when it's in water with salt, okay? So it depends on the amount of salt, of course, and it depends on other factors like the sequence and the length. But basically, the DNA denaturing temperatures are around 85 degrees centigrade. So you could imagine once we had temperatures below 85 degrees centigrade. So throughout the Archean, the temperature of the ocean surface was cooling. And that's because, well, some of the greenhouse gases were being used up. And also because the sun was also becoming warmer. Remember that the Archean is 1,000 million years. So in 1,000 million years, there has also been some increase in the surface area of the sun and therefore warming of the surface. But we had a lot of greenhouse gases. So that kept the ocean very warm. But as these greenhouse gases were being used up, the ocean surface started cooling down. And they also have that in sediments also. They can determine at different points in the Archean what the temperature was. And the temperature was slowly decreasing over the Archean. So once the temperature of the ocean surface got below about 85 degrees centigrade, then what we would find is that strands of DNA would connect with their complementary strands and then form this double-strand DNA. And therefore, once you had double-strand DNA, you could no longer replicate. So they would just stick together and we wouldn't have a replication. But as you can imagine that when the sun came out and warmed up a little bit the ocean surface because of the absorption of infrared light on the ocean surface, and also because of the absorption of the ultraviolet light in these DNA molecules, that would be sufficient to denature DNA, this molecule. And when we do denature it, we find that it absorbs stronger in this UVC range. We get this increase, about 30 to 40% increase in the absorption when DNA is denatured. And that is just because the bases open up, you know. In this form, they are piled one on top of the other. So they are somehow shielded to the ultraviolet light, which is coming in. And in this case, they are less shielded, so they start absorbing more. So this is a very well-known phenomena. And the biologists use it all the time to determine the concentrations of single-strand or double-strand DNA. And it corresponds to about 40% more in the single-strand case. So we are absorbing more. And as soon as we denature, we start absorbing more light in the ultraviolet. And that will cause the temperature, a local temperature, to heat up, and then we can have denaturing. And then at night, temperature of the ocean surface cools down, and there's none of this ultraviolet light. And so we can have renaturing with segments, strands of DNA floating on the ocean surface. And so we can produce these two double strands where we had at the beginning only one single strand, without using any complicated enzymes. So this is only using the physical mechanisms which were available. That is the hot ocean surface temperature, the ultraviolet light, and the cooling, this cooling cycle at night, which allows us to do the extension or the renaturing of DNA. So this is template directed, because these single strands act as template to form another complementary strand. And then when it divides again, the complementary strand can act as a template, and the original strand can act again as a template. And so we have replication. In fact, this is exponential replication. So we have one in the first period, and in the second generation, we have two, and then in the third generation, we have 4, 8, 16, 32, 64, so on. So we have an exponential increase. So this is an autocatalytic photochemical reaction. And it's autocatalytic because one of the strands is acting as a template to produce the other strand. And it also ties photon replication to, DNA replication to photon dissipation, and therefore entropy production. So we know for any process, and of course, replication is a process. Any process only occurs to produce entropy. So we're having a replication, which is tied to photon dissipation. When it denatures, we have this increase in the photon dissipation. And then when we have two, where we had one before, we're also increasing the dissipation. So we always, whenever we talk about evolution, we have to look at if dissipation is increased. But remember, as I said, we don't necessarily have to have it as so. We can go backwards. We can go to a system in where we have less dissipation. For example, when we go to this branch of the Barnard cell, where we have less dissipation, that can occur, but the probability is less. So in general, the probability in evolution is towards systems which are ever more increasing in dissipation. So you might say, oh, okay, this sounds nice and maybe it'll work, but you haven't proved it. Well, we actually did the experiment. So here we have ultraviolet light, UVC range, which is coming in through an optical cable. And then we have DNA in this temperature holder. And DNA is in a quartz cuvette. Quartz because it lets ultraviolet light pass. Glass would not let ultraviolet light pass. Glass would be absorbing ultraviolet light. But water and quartz do allow ultraviolet light in this longitude, this wavelength range to pass and be absorbed on the DNA, which we have in this temperature controller. And this controller is controlled by a computer, so we can put whatever temperature we like, the substance. And then we just measure the absorption spectrum with this spectrometer. It's a very small spectrometer, but it does the job for us. So this measures the absorption, and this also measures the scattering, because there's a small amount of scattering of light over DNA, but it's very small, so we can effectively ignore it. And in fact, we did ignore it, because in the end, we were not getting very useful data out of this spectrometer. So this is the setup that we have, and these are the pipettes, which are used to measure the exact quantities of DNA. So we know how much DNA is in each of these cuvettes, and we just measured the absorption spectrum. So are there any questions about this experimental setup? Ivan knows it because he, in fact, did his bachelor's thesis over this experiment with this experimental setup. But Andres, Claudette, do you have any questions?
In which part is the sample? I don't understand that. I
The,
didn't
the
understand.
sample, the sample is here.
Okay, in the black.
Yeah, it's
Okay.
covered so you don't see it because this ultraviolet light is dangerous for our eyes.
Okay.
So we have a cover on it. And so this, we don't see the scattering of the ultraviolet light. We always have to turn the ultraviolet light off when we change the material, the DNA sample. But the sample is here in this chamber.
Okay.
This chamber is used to control the temperature, and we have also water flow through the chamber, which allows us to remove heat rapidly from the system. So if we want to go from, let's say, 85 degrees centigrade to 50 degrees centigrade, we can do that very rapidly with this water flow, which is like a little radiator. So we have a pump here in water, which is pumping the water through the system and allowing it to cool in this reservoir. And that allows us to control the temperature very finely within plus or minus 0.01 degrees centigrade and go rapidly from one temperature to another. So that's the other component which I didn't really talk about. Okay, Andres, you have a question?
Yes, the sample is just RNA or DNA sample, but
Yes.
from where from or how do you
Okay.
put it on the black dispository?
Okay. Well, yes, it's just pure DNA, and it can be salmon sperm DNA, which is in fact something that the biologists use just because it's very easy to obtain salmon sperm DNA. You can also obtain fresa, strawberry DNA, the fresas. It also has a lot of DNA and it's very easy to obtain also.
I also hear once that it's easy to obtain from onions.
I didn't know that.
Yeah, from bananas.
I guess from any vegetable, no, it should be rather easy to obtain. But like the basic ones which are used in the laboratory are salmon sperm DNA and strawberry DNA. I guess because they are the easiest ones to obtain, or the cheapest ones to obtain. But what else? But what we also did, not only the salmon sperm DNA, but we also used synthetic DNA. So this is DNA which you produce in the laboratory. And this was produced in Fisiología, se llama el Instituto de Fisiología in la UNAM. And they produced us. So we actually gave them a sequence and they produced the two strands. The strand corresponding to the sequence and it's complementary. Because you know this is 3' to 5' and 5' to 3'. So they're a little different. The two complementary strands are actually a little different, but they are determined by us, and we give the sequence to Fisiología, and they produce it for us, and we pay them a little bit, like 3,000 pesos, I think is what we paid for our DNA samples. So we had actually 25 base pair DNA. So I'll show you that in this slide. This is for 25 base pair DNA, synthetic DNA. And so that corresponds more or less to about this size. I think this is about 25 pairs of DNA here in this strand. And this is the absorption spectrum as a function of temperature. And so we see the peak at 260 nanometers. And I remind you that this is exactly the energy which was coming into Earth's surface at the beginning of life, 260 nanometers. And it's absorbing very strongly there. And as I mentioned, there's this hyperchromic effect when it goes from double strand, which is the black line here, to single strand, which is the blue line here. And that happens by increasing the temperature from 30 degrees centigrade to 80 degrees centigrade. For this 25 base pair DNA at 85 degrees centigrade, or close to 80 degrees centigrade, all of the double strand is denatured into single strand. And that's why we get this increase in absorption of about 25% here in this case. Okay, so these different lines correspond to different temperatures that we did this absorption experiment. So we just put the DNA in the water and we have the UVC light coming in and we measure the absorption as a function of wavelength. So this spectrum allows us to measure the wavelength, determine the wavelength, and we just plot the wavelength versus the absorption. I call this extinction because, as I mentioned, there's also a little bit of reflection, not only absorption. So there are two methods to reduce the light which is getting to the spectrometer. One is through absorption of the DNA, and the other is reflection on the DNA. But the reflection is only a very, very small part, maybe 1 in 1,000 of what the absorption. So we just ignore it for the experiment. So this is how the absorption spectrum changes as a function of temperature of the water. And basically what's happening is double strand is going into single strand. Now we can also do different temperatures around these temperatures, very close, 3-degree bin around these temperatures, so 1.5 degrees above 30 degrees centigrade and 1.5 degrees below, and then plot that. And that is these graphs here, which we see on a different scale. This is the different spectrum of temperature at, let's say, this would be 28.5 degrees centigrade and 31.5 degrees centigrade. That would correspond to the black line here. Okay, so that is this spectrum. That's the different spectrum, changing temperature by about 3 degrees centigrade. And we do that around all these temperatures, and these are the spectra that we obtain. Okay, so this is the different spectra between partially denatured DNA at different temperatures and DNA not denatured. Okay, well, at the 3 degrees. So whatever partial denaturing is at minus 1.5 from whatever is at 1.5 degrees above that temperature. Okay, is that clear? Are there any questions on this graph? Claudette?
Sorry?
Do you have any questions about the
For
graph?
the moment, I don't think so, but maybe in the future I'm going to have.
Okay. Well, you see that I have a question for you then, if you're not going to ask me. So you see that the absorption spectrum is increasing here. We can only go down to about 210 nanometers because our spectrum, our physical apparatus doesn't allow us to go lower. But in fact, DNA also increases, absorption increases more towards this end. But we're only getting light about 220 nanometers coming into Earth's surface. So do you know why DNA is absorbing very strongly at shorter wavelengths, Claudette?
Well, I think that is because, well, I don't know if there is in the process where, well,
It's absorbing at 260 because of electronic excitation, collective excitation of the ring. No? So we're getting like a pi to a pi star excitation. But here
the minimum.
we're having something else which is going on here.
Yes.
Can anybody tell me? Why is
the first is the wrong state?
Well, it's going into an excited state, and that's excited state is decaying. Maybe not necessarily to the ground state. In this case, see it decays to the ground state. But here, with that pista, can anybody tell him? If I tell you it's not exactly going to the ground state, what is in fact happening here? Remember what I said that about shorter wavelength radiation can be dangerous to DNA.
Yes.
Why?
Because well, it is more energetic, and it make like a vibrate states,
What kind of states?
vibrational.
No, no. Here we are electronically exciting with a photon. So the vibrational states don't get excited. They get excited later through the conical intersections. But we're exciting the electrons only. So it's electronic excited state. Okay, can you maybe, if I tell you something is happening to DNA, you know, we're starting to destroy it in this region. Can you imagine what would go first? What would be the first like particles to go off from DNA?
It's because of ionization.
Ionization, yeah. These are electrons which are being lost to DNA. So slowly you're going to start destroying the DNA structure. You don't have the same tautomer anymore. And so this is dangerous. So that could be a good reason, for example, why life did not start on Mars. Because on Earth, we had hydrogen sulfide absorbing in this range. And we have also carbon dioxide absorbing a little bit. We probably also had carbon dioxide on Mars at the beginning of life on Earth. But probably, like today, there's not enough carbon dioxide because the atmosphere is so thin that this light would have been coming into Mars, on the surface of Mars, and destroying these molecules. So this is like a range, which we call a sweet range or un rango dulce, between about 210 nanometers and about 285 nanometers, where we have enough energy to remake these molecules, but not enough energy to ionize them. So here, in fact, we are destroying them. So they don't go back to the ground state. They go back to some other state, which is an electron tautomer of the DNA without an electron or two electrons. And they don't become the same as absorbing. So it's important that we stay out of this region for producing these fundamental molecules of life. Okay, Andres, do you have a question?
Yes, so with the sample you put on the experiment, you obtain this graph of absorption.
Yes.
But I didn't understand when it's denaturalized and when it's on double.
Okay. Well, it depends on the temperature. So here we have
on the graph, the part from below. It's when it's denaturalized depend on the temperature. I mean the green and the black.
This is when it's double strand. This corresponds to double strand. And when we increase the temperature, we get the single strand. In between, we have partially denatured. Some is single strand and some double strand. Or even different parts of the molecule can be single strand and different parts double strand. Okay, so at the bottom here, at the cold temperatures, we have double strand DNA. And at the warm temperatures, hot temperatures, we have single strand DNA. And we get this hyperchromic effect because the bases are wide open. It's like unfolding an umbrella. We can absorb more light.
And the other graphs.
These other graphs, okay, these other graphs are difference between different temperatures. So, for example, the first graph here, which is in black, I believe, here at the bottom, this corresponds to 30 degrees centigrade. And so we take one run at 31.5 degrees, and then subtract it from 28.5 degrees. So we're looking at a range of 3 degrees at 30 degrees centigrade. Un rango de 3 grados alrededor de 30 grados centígrados. Y esa es la diferencia que estamos graficando. Ok. Entonces encontramos que la diferencia es mayor cuando estamos en este rango. Y I have trouble figuring out, this looks like red, no? This one here, which corresponds to 70 degrees centigrade. So we get most denaturing at around 70 degrees centigrade. So this is the rate of denaturing per degree centigrade. So we get an increase. This is a bigger spectrum than this spectrum at 30 degrees centigrade. So this is just to show how at different temperatures, how the denaturing occurs, and it occurs greater at higher temperatures than at lower temperatures. Okay?
Okay.
Okay, Iván, una pregunta.
Let me think how to say it.
Okay.
Okay, first, the ionization of the DNA depends
Yes.
on temperature, no?
It's
Because,
some
for
what?
example,
Okay.
depends on temperature.
At some temperature?
Yes, because, for example, at 30 degrees,
Uh-huh.
there's no increment in the absorption, in the difference spectrum.
Uh-huh. This different spectrum here? Or
It-
ionization. This is this spectrum here.
but for example, the black spectrum
Uh-huh.
doesn't have the increment at lower wavelength.
Doesn't have what? Sorry?
Increment.
Increment. Here, you mean here, where I'm showing the pointer?
No, at lower wavelengths.
Even lower, here.
Well, for example, the blue one is increasing at the same time we decrease the wavelength.
The blue one is increasing, decreasing the same time as we increase the wavelength. Are you talking about this? Oh, okay. And so
But the black one and the red one don't do
yeah,
that.
well, okay, we have to be careful here also because this is actually where our spectrum ends. The spectrometer doesn't measure. And also this is where our light output ends. So here in this region, that's why it's not so well defined. You can see the movements up and down and these peaks here. Some of these may be a physical effect which is occurring because depending on the temperature, there are different types of base pairs which are denaturing. So it could be, for example, that guanina and cytosina are denaturing at high temperature because there are actually 3 hydrogen bonding between guanine and cytosina. And adenina and thymina are denaturing at lower temperatures. So they have different spectrums, no? So this is part of this spectrum is the denaturing. But also here, when we get to ionization, we're getting very little light. So that's why we have large fluctuations. So I wouldn't be confident in anything here, no, about this light. I think we should ignore what's happening in the ionization region. We shouldn't be speaking about it because we don't really have the tools to determine exactly what is going on here at lower. Okay, you see the light spectrum. We can show the light spectrum. It runs out at about 210. So we're not getting any photons out of the source. So we don't have good statistics here to take a graph here. Okay, I'm not sure if that answered your question.
Yes, because I had that question the last 2 years.
Oh, on the exam of your,
Yes, but
I don't remember that.
I think it's not very important, but I had forgot it, but now I am see it again.
Okay.
I remember that I had that question.
Okay. Yeah, so this is just the ionization region, but we really need other instruments to be able to figure out what's going on there. Okay.
Okay, thank you.
Okay. So let me go to the next slide now. This is the case.
The ionization occurs because of the energetic photons that
Yes.
take away some electrons from.
Yes.
Okay.
Exactly. Yeah. So removing electron from the molecule through the energy in the photon, because these energies are increasing as we go to lower wavelengths. Okay, so that was denaturing using temperature. Now, what about light-induced denaturing? So in this case, this is the case of the salmon sperm DNA. We also did synthetic DNA. So this is also the case for synthetic 25 base pair DNA. And now in the case of this was the case of denaturing due to heat, due to temperature. Now, getting back to this idea of denaturing using light. So what we did in this case, this experiment, is that we raised the temperature to 40 degrees centigrade. And then we turn the light off and on. Okay, so when we turn the light off, we don't get any data because there's no light going to the spectrometer. And then we waited for about half an hour and then we turn the light on again. The up arrows refer to turning the light on and the down arrows to turning the light off. And this is again the extinction. So we're plotting the same as we're plotting on this graph, but we're integrating from about 255 to 265. So we're integrating this region here. Okay, so this is the integration of 255 to 265 nanometers and plotting the extinction in this range as a function of time in the experiment with the light being turned on and off. So when we turn the light off, we find that the extinction goes down until we turn the light on again. And then it starts going up and down and up and down and up and down with the light being turned on and off. So we see, and this is at a constant temperature, so we're controlling the temperature in this system at 40 degrees centigrade, so it's being fixed. And so we're actually seeing light-induced denaturing. So we're seeing that this can occur, this UVC light-induced denaturing of DNA can occur. Okay, and this is the same for 25 base pair DNA, but this is now as a function of wavelength. So instead of integrating from 255 to 265, we're plotting the different wavelength results. So this is, and this in fact is the difference. So this corresponds to this difference spectrum here that we saw here for the temperature denaturing. This is for DNA denaturing using ultraviolet light. So we're plotting the difference here, the spectrum which was taken when at the end of the light on period compared to the light, the beginning of the light on period. So we're taking this difference of the spectrums and then plotting them. So we see again that we find that light-induced denaturing as a function of wavelength. And we see for these solid lines correspond to double-strand DNA, so we see denaturing. And the dotted dashed lines correspond to single-strand DNA, so we don't see any denaturing. In fact, we see a decrease in the extinction after the light-on period. So it's not denaturing, because remember, denaturing gives an increase in the extinction, an increase in the absorption. But we, in fact, for single-strand DNA, we find a decrease. And we assume that that is because we're producing thymine dimers, which are these other molecules, those thymines which are together in the sequence, they reduce the absorption. And in fact, thymine dimers do absorb or reduce the absorption at about 275 nanometers. So we're getting single strand, which is forming these dimers, and double strand, which is denaturing. And it's also forming dimers, but we don't see that because we get much more denaturing than we get the formation of dimers. Okay, I think they're about to throw us off, and this will be the last session, okay, for today. But if any of you have any questions, please ask me about this slide. So is this slide understandable? ¿Es entendible este acetato? Andrés?
Sí, creo que sí.
Okay. So I have to ask you a question. You don't have any questions. So this is double strand, right? And we also did it as a function of temperature, but keeping the temperature constant. And we get greater ultraviolet light induced denaturing the higher the temperature. So this spectrum goes up. So why would you expect at a higher temperature, UVC light can denature more than at lower temperature? Why would you think that, Andrés? ¿Por qué pasa que a altas temperaturas la denaturación es mayor con luz ultravioleta que a bajas temperaturas? ¿Sí entendiste la pregunta?
Sí, me imagino que la desnaturalización pues se da más fácilmente a mayores temperaturas porque es más fácil separarlas, no sé cómo se hagan
Por
la
los
unión,
enlaces.
ajá, los
Sí.
enlaces
Los enlaces de hidrógeno.
entre
Sí.
las dos cadenas son de hidrógeno, es más fácil.
Exacto, sí. Sí, es más fácil porque la molécula está vibrando más rápidamente a temperaturas altas. Entonces es
Sí.
mucho más fácil que se separa. Igual que pasó en la denaturalización por pura temperatura. Obviamente, la mayor la temperatura, mayor es la denaturalización, ¿no? So, es igual en este caso, la mayor la temperatura, la mayor probabilidad de un fotón pueden causar más denaturing. Okay, in fact, if you look at the graph as a function of temperature, it goes up very quickly. So this is the amount of denaturing. This is in percent per hour of denaturing of this 25 base pair, double strand, DNA. And this is how the increase in denaturing goes with temperature. So the greater the temperature, the greater this effect on the ocean surface of denaturing. So that is in fact what we want. We want in the daytime that we get greater denaturing than in the nighttime. In the daytime, the temperature of the ocean surface is warmer. And also we don't have any ultraviolet light at night. Okay. Claudette? ¿Tienes
Yes.
una pregunta sobre
Yes.
esto? Ajá.
Okay, if you're saying that, well, temperature is, okay, then the denaturation is direct proportional to temperature, right? Well, not direct, but like an exponential, but it's proportional.
Well,